13.8 billion years ago, the universe began. In a single, incomprehensible instant, everything that exists today, every atom, every ray of light, every fundamental law of physics, emerged from what was essentially nothing. In one moment, there was no space, no time, no matter. In the next, there was everything. Just how such a thing is even possible remains perhaps the greatest mystery in all of science, one that transcends disciplines and blends cosmology, quantum physics, and philosophy into a single, confounding question. Everything we know about the universe hinges on principles like mechanism, causality, and logic. We yearn to understand why things are the way they are. And yet, when we look back to the very origin of everything, we encounter a silence, a blank slate, no explanation, no process, just an abrupt, infinite unfolding. At the most fundamental level, we simply don't know how or why the universe came into existence. But this lack of an explanation isn't for lack of trying. Scientists, philosophers, and dreamers alike have long pondered the question: what was there before the universe? Some, like the legendary physicist Stephen Hawking, offered a startling possibility. Perhaps there was truly nothing before. Not nothing in the sense of empty space, but a deeper nothing, the absence of space and time themselves. According to this idea, space and time are not separate entities, but deeply intertwined properties of the universe we inhabit. So when we speak of the beginning of the universe, we're really talking about the beginning of time itself. There was no before the Big Bang, because there was no time in which before could exist. It's like asking what's north of the North Pole. The question itself loses meaning. Hawking proposed that as we trace space-time backward to its earliest moments, we find it warping and curving inward until it smoothly rounds out. There's no singular beginning, no edge or boundary to cross, just a kind of smooth transition from non-existence to existence. From a certain perspective, the universe simply is. It didn't necessarily come from anywhere in the traditional sense. Of course, not everyone agrees. Other scientists suggest that the Big Bang was just one part of a much grander and more complex story. According to the theory of cosmic inflation, our universe underwent a split-second period of exponential expansion immediately after it began. This inflation smoothed out the universe, giving rise to the cosmic structure we see today. But some physicists believe this inflation never truly ended, not everywhere at least. Instead, they propose that inflation is still happening, eternally, in different regions of a vast, ever-growing multiverse. In this vision, our universe is just one bubble among countless others, each with its own laws of physics, dimensions, and even timelines. Some of these universes might be wildly different from ours, while others could be eerily similar. This idea, the eternal inflation model, opens the door to the tantalizing concept of a multiverse, a sprawling ensemble of universes that extends far beyond what we can observe. If this is true, then the Big Bang wasn't the beginning of everything, just the beginning of our particular bubble. Yet another theory, known as the Big Bounce, suggests something even more cyclical. According to this model, the universe didn't begin from nothing, but instead emerged from the collapse of a previous universe. The cosmos expands, contracts, and rebounds in an infinite loop. No beginning, no end. Just an eternal rhythm of creation and destruction, woven into the very fabric of existence. These aren't just fanciful ideas. They're grounded in real physics, drawn from the mathematics of general relativity and quantum field theory. And yet, no single theory has emerged as definitive. That's partly because we're limited in how far we can see. The cosmic microwave background, the faint afterglow of the Big Bang, marks the edge of our observational horizon. Anything that happened before that moment is hidden from us, perhaps forever. Still, scientists continue to push the boundaries. New telescopes, like the James Webb Space Telescope, are probing deeper into the early universe than ever before. They are not just looking for galaxies, they're looking for clues. Clues about the first stars, the first structures, the very conditions that may reveal what triggered the cosmic explosion that set everything into motion. Perhaps someday we'll find the answer. Or perhaps we'll learn that the question itself is flawed, that there's no why to the universe, only the raw, beautiful fact that it is. Whatever the truth may be, the mystery of the universe's origin remains one of the most awe-inspiring topics in human inquiry. It invites us to peer beyond the veil of time, to wonder, and to imagine realities beyond our own. Some strange, some familiar, all woven into the silent infinity that surrounds us. As we trace the early moments after the Big Bang, we arrive at a state of unimaginable density and temperature, a chaotic, seething soup of raw energy. There were no stars, no galaxies, not even atoms. Just a glowing fog of particles and forces interacting violently in an arena where the familiar laws of physics began to take shape. In this cosmic furnace, quarks and gluons, the fundamental building blocks of matter, jostled and collided. The four fundamental forces we know today, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, began to separate from one another. The universe was expanding at a phenomenal rate, and with every microsecond, it cooled just enough for new physical processes to occur. It was a chain reaction, one phase transition after another, each more structured than the last. But the most astonishing part is that this emergence of order came from sheer chaos. Quantum fluctuations, tiny, random disturbances in the energy field, left their fingerprints on the very fabric of space-time. These quantum ripples, born in the smallest scales imaginable, would later give rise to the vast cosmic structures we see today. Clusters of galaxies, voids of darkness, and filament-like webs of matter stretching across the cosmos. It's a profound truth. The seeds of galaxies were sown by quantum randomness. As the universe continued to expand and cool, subatomic particles began to bond, forming the first protons and neutrons. Within the first 3 minutes of cosmic time, these protons and neutrons fused to form the nuclei of the lightest elements, hydrogen, helium, and traces of lithium. This process, known as Big Bang nucleosynthesis, set the stage for everything that followed. And it all happened in mere minutes. But the universe remained dark. The temperatures were still too high for electrons to combine with these atomic nuclei to form complete atoms. The result was a hot, dense plasma of charged particles that scattered light in every direction. The universe, in its infancy, was opaque, a brilliant, blinding fog that no photon could escape. This phase lasted for nearly 380,000 years, until the universe cooled just enough for electrons to settle into orbit around nuclei. This event, called recombination, allowed light to travel freely for the first time. Those first photons still exist today as the cosmic microwave background, a faint, ghostly afterglow that permeates all of space and provides us with our earliest snapshot of the cosmos. Captured by satellites like COBE, WMAP, and more recently Planck, this ancient light reveals a near-perfectly uniform universe with tiny imperfections. And it is within those subtle imperfections that we find the blueprint of everything. Gravity began to work its magic, drawing matter into denser regions and leaving emptier regions to become the great cosmic voids. Over millions of years, those denser regions collapsed under their own weight. Clouds of hydrogen and helium gas began to form, pulled together by the irresistible force of gravity. The first stars were born, titanic, short-lived giants that burned with incredible intensity and forged the heavier elements in their cores. When they died, they exploded in cataclysmic supernovae, seeding the universe with carbon, oxygen, and iron, the elements necessary for planets, life, and everything we know. These stars gathered into the earliest galaxies, vast collections of stars, dust, and dark matter swirling together in dynamic harmony. The universe was no longer a dark fog. It had become a place of light, structure, and unfathomable scale. Yet we must not forget the mysterious players that shaped this entire evolution: dark matter and dark energy. While ordinary matter, the kind that makes up stars, planets, and people, accounts for less than 5% of the universe, the vast majority remains invisible and unexplained. Dark matter, though never directly observed, exerts gravitational influence on galaxies and clusters. It acts like an invisible skeleton, helping galaxies hold their shape and orbit faster than visible mass would allow. Without dark matter, our universe would look radically different, perhaps not even capable of forming galaxies at all. Then there's dark energy, a far more elusive entity. Discovered in the late 1990s, it's responsible for the accelerated expansion of the universe. Unlike gravity, which pulls things together, dark energy pushes them apart, causing galaxies to race away from each other faster and faster over time. Together, dark matter and dark energy dominate the cosmic narrative. They shape the past, present, and likely the future of the universe. And yet, their true nature remains one of the greatest scientific enigmas of our time. We are, in every sense, the byproduct of cosmic processes, shaped by forces we barely understand, and nurtured by the long dance of energy and matter. From the flicker of quantum fluctuations to the birth of galaxies, the universe has been on a journey of astonishing transformation. And through all of this, we've only recently arrived to witness it. As the universe matured, galaxies began to organize into vast structures. Threads of matter stretched across incomprehensible distances, forming what scientists now call the cosmic web. This immense network of filaments, voids, and clusters reveals a grand architecture shaped by gravity over billions of years, a skeleton upon which the visible universe is built. But how did this colossal structure emerge from the randomness of quantum fluctuations? The answer lies in gravity's relentless pull, a patient force that over cosmic time transformed minute imbalances into galaxies, clusters, and superclusters. Picture the early universe as a vast ocean of mostly uniform density, but with tiny ripples, overdense regions, seeded by those initial quantum perturbations. These overdensities had just enough mass to attract more matter. Over time, as the universe cooled and expanded, those regions grew denser. They became the birthplaces of stars and galaxies. As matter clumped together under gravity, it also dragged surrounding matter toward it, creating elongated filaments that connected clusters like tendrils in a spider's web. What emerged was not a random scatter of galaxies, but a finely patterned tapestry. This structure, visible in large-scale surveys like the Sloan Digital Sky Survey, resembles a three-dimensional web stretching hundreds of millions of light-years across. And yet, this cosmic web is far from uniform. The vast voids between filaments, some stretching for hundreds of millions of light-years, are almost completely empty. These voids are among the most mysterious regions in the universe. They represent areas where matter is so sparse that galaxies are rare and time seems to flow differently. Some cosmologists even speculate that these voids might one day offer portals to test the fundamental laws of physics away from the noisy complexity of matter-rich space. At the intersections of filaments lie galaxy clusters, the densest regions of the cosmic web. These clusters can contain thousands of galaxies bound together by gravity and swimming in hot gas. They are the largest gravitationally bound structures in the universe and act as cosmic laboratories, helping scientists understand everything from dark matter to galaxy evolution. But the cosmic web doesn't just define structure, it influences motion. Galaxies aren't simply drifting aimlessly through space. Their movements are guided by the gravitational contours of the web. We now understand that our own Milky Way is not isolated, but part of a vast supercluster called Laniakea, meaning immeasurable heaven in Hawaiian. This supercluster spans over 500 million light-years and includes more than 100,000 galaxies. Laniakea itself is just one branch of an even larger structure, the dipole repeller and great attractor, regions of space that either repel or draw galaxies in vast cosmic flows. Incredibly, our galaxy is currently moving at about 600 kilometers per second through space, pulled by the gravitational influence of distant clusters. To map this structure, astronomers use techniques like redshift surveys, where the light from galaxies is measured to determine how fast they're moving away from us. Combined with gravitational lensing, the bending of light by massive objects, scientists can reconstruct a 3D map of the universe's layout and better understand the invisible forces at play. As we study this map, we also begin to ask deeper questions. Why this structure? Why these laws? Why does matter arrange itself in filaments and not in some other way? These patterns might be dictated by the fundamental constants of the universe. Values like the gravitational constant, the speed of light, and the mass of particles. Even small changes in these constants could result in a very different cosmos. Perhaps one incapable of forming stars or galaxies at all. The structure of the universe, it seems, is not only shaped by physical laws, it also shapes the possibility of life, consciousness, and complexity. This has led some physicists to explore the idea of a fine-tuned universe, the notion that the conditions of our cosmos are precisely set to allow for intelligent life. While controversial, this idea invites profound contemplation. Are we simply lucky inhabitants of a universe with the right rules? Or is there a deeper reason why the cosmos appears designed for observation? Adding another layer of intrigue, the cosmic web may even affect how galaxies evolve. Galaxies within dense filaments tend to grow faster, collide more often, and experience higher rates of star formation. Meanwhile, those isolated in voids evolve slowly, more peacefully, with less dramatic encounters. In this way, a galaxy's environment can determine its destiny. Modern simulations, like the Illustris and Millennium projects, recreate these cosmic structures in powerful supercomputers, modeling billions of particles of dark matter and gas over cosmic time. These simulations confirm what we see in telescopes, but they also hint at structures beyond our view, suggesting the universe may be far larger and more complex than we can currently observe. Ultimately, the cosmic web is more than just a map of galaxies. It is a living record of the universe's history, a fossilized imprint of gravity at work, sculpting the cosmos over 13.8 billion years. And within this grand design, we find ourselves not at the center, but as part of the pattern. A single strand in the web of infinity. Our journey now shifts from the grand architecture of the cosmic web to one of its most iconic nodes, our very own galaxy, the Milky Way. A barred spiral galaxy stretching over 100,000 light-years across. The Milky Way is home to hundreds of billions of stars, planets, clouds of gas, nebula, black holes, and, perhaps most significantly, us, the only intelligent life we currently know of. At its heart lies a mystery, a supermassive black hole known as Sagittarius A, weighing in at over 4 million times the mass of our Sun. Invisible yet powerful, this dark titan shapes the orbits of stars at the galaxy's core and drives dynamic processes that influence the entire structure of the Milky Way. And yet, black holes like Sagittarius A are not rare. Nearly every large galaxy we observe harbors one, suggesting they are not just byproducts, but key players in galactic evolution. The Milky Way itself is a rotating, majestic disk filled with spiral arms that wrap outward from the center like cosmic whirlpools. Each arm is a cradle of star formation, glowing with young stars and nebulae. Our solar system resides within the Orion Arm, a relatively quiet neighborhood that has allowed life to flourish in stability. But our galaxy is far from isolated. It is part of a smaller galactic group known as the Local Group, which includes about 50 galaxies, most of them small dwarf galaxies orbiting larger ones like the Milky Way and the Andromeda Galaxy. Andromeda is our closest galactic neighbor, located around 2.5 million light-years away. It is similar in size and structure to the Milky Way, and is on a slow-motion collision course with us. In about 4 billion years, the Milky Way and Andromeda will merge in a titanic galactic collision. Despite the vast number of stars in both galaxies, the actual chance of star-to-star collisions is almost zero due to the immense distances between them. Instead, the gravitational interactions will create a stunning cosmic ballet: spiral arms twisting, black holes coalescing, and gas clouds compressing to ignite new waves of star formation. The end result? A new, larger elliptical galaxy, often referred to by astronomers as Milkomeda. But let's zoom out further. Beyond our local group lies the Virgo supercluster, a gravitationally bound structure stretching across 110 million light-years. This vast region contains thousands of galaxies and clusters. And yet, even the Virgo supercluster is not the final word. It is part of the Laniakea supercluster, the immense galactic continent that we explored in Segment 3. Each level of cosmic structure, from solar systems to clusters of galaxies, tells a story of gravitational assembly, of smaller things coming together to form larger, more complex systems. These structures weren't always there. They were built over billions of years by the subtle warping of space-time, by matter's relentless pull, and by the expansion of the universe itself. Now let us venture even further to the observable edge of the universe. Light, as fast as it travels, takes time to reach us. When we look at galaxies billions of light-years away, we're looking back in time, seeing them as they were when the universe was young. The Hubble Ultra-Deep Field, for instance, captured light from galaxies more than 13 billion years old, revealing their faint glows like candles flickering at the dawn of time. And yet, the observable universe is only a portion of what exists. Beyond the cosmic horizon lies the unobservable universe, regions of space so far away that their light hasn't had enough time to reach us since the Big Bang. It's entirely possible, and even likely, that the universe stretches on infinitely in all directions, filled with galaxies we will never see, civilizations we will never meet, and mysteries we can only dream of. The vastness is almost paralyzing. It's easy to feel insignificant in the face of such scale. But there is another way to see it. We are not separate from this cosmos. We are of it. The atoms in our bodies were forged in stars, the air we breathe shaped by supernovae, the iron in our blood born in the death of ancient suns. We are, quite literally, the universe made conscious, a way for the cosmos to know itself. As Carl Sagan so eloquently said, we are a way for the cosmos to know itself. When we look at the stars, we're not just gazing outward, we're gazing inward, reconnecting with a story that stretches across eons. The Milky Way is not merely our address, it is our shared inheritance. And as we chart its stars, as we launch telescopes to capture its light and send spacecraft to explore its planets, we are not just observers. We are participants in a journey that began before time and will stretch far beyond our lives. From the elegant dance of spiral arms to the galactic collisions that reshape the night sky, the story of galaxies is the story of creation itself. a slow, majestic unfolding that gives birth to stars, worlds, and ultimately wonder, time. It's the one dimension we all move through together, in one direction, at the same speed. But in the context of the universe, time becomes far more than a ticking clock. It's a force that shapes the cosmos, sets the rhythm of galaxies, and determines the ultimate fate of everything. The concept of time's arrow, the one-way flow of time, is intimately tied to the expansion of the universe. Ever since the Big Bang, space itself has been stretching, dragging time along with it. The farther we look into the cosmos, the further back in time we see. Distant galaxies are time capsules, their light revealing a younger universe, full of hot stars and turbulent forces. But why does time move forward? According to physics, most fundamental laws are time-symmetric. They don't prefer a direction. What gives time its irreversible quality is entropy, the gradual increase of disorder in a system. The universe began in an incredibly low entropy, high-order state. As it evolves, entropy increases. Stars burn out, galaxies disperse, and order breaks down. This growing disorder defines time's flow. This progression has led to a cosmos in motion, but that motion isn't endless. Scientists now know that the universe's expansion is accelerating, driven by the elusive force of dark energy. As galaxies drift farther apart, space itself grows faster than gravity can keep it together. Over cosmic time, galaxies will recede beyond each other's light, vanishing from view. This leads us to one of the most fascinating questions in cosmology. What will become of the universe in the end? There are several competing theories. The most widely accepted scenario is the heat death, or the Big Freeze. In this model, the universe continues to expand forever. Stars eventually burn out, galaxies fade, and black holes evaporate through a process known as Hawking radiation. Over unimaginable timescales, trillions of years, the cosmos becomes cold, dark, and lifeless. Entropy reaches its maximum, and time itself may cease to have meaning. Another possibility is the Big Rip. If dark energy strengthens over time, its repulsive force could eventually overcome all other forces, tearing galaxies, stars, planets, and even atoms apart. The very fabric of space-time would be shredded in a final catastrophic end. It's a dramatic vision of destruction, but one still being debated in theoretical physics. There's also the possibility of a big bounce, a cyclical universe that expands, contracts, and re-expands endlessly. In this model, our universe could be just the latest iteration in an eternal loop of birth and rebirth. Time would still have an arrow, but its scope would be infinite, looping endlessly in cycles too vast for us to grasp. Then there is a theory that rewrites everything: the simulation hypothesis. What if time is not a fundamental property of the universe at all, but an emergent phenomenon, a byproduct of how we process information? In such a scenario, time may be an illusion, and the universe itself could be a kind of hyper-advanced computation. While still speculative, this idea forces us to rethink not just time, but reality itself. No matter the model, what becomes clear is that the universe is not static. It's in transition. Galaxies are not fixed in the sky. They are fleeting features in an ever-changing tapestry. Stars are born, live, and die. Black holes form and vanish. Even space itself, once thought to be a passive backdrop, is an active player in the universe's story. And through all of this, we find ourselves in a rare and precious moment. A time when stars still shine, galaxies are still visible, and life can exist. We live in the stellar epoch, a brief window in the universe's timeline where complexity is still possible. Future civilizations, if they exist, will face a different cosmos. In 1 trillion years, all but the closest galaxies will have disappeared from sight. Without the cosmic microwave background to study, Without other galaxies to observe, those distant scientists may never know the true nature of the universe's expansion. For them, the universe may appear small, static, and eternal, a cosmic illusion caused by a lack of evidence. But we live in a privileged era, one where we can still read the universe's past in starlight and map its future in equations. An era where we can ask, where is all this going? And just as entropy increases in physics, so too does knowledge in science. Every discovery adds to our understanding of time's trajectory. Every theory brings us closer to glimpsing the ultimate fate of all things. Still, the most profound truth may be this: even if the universe fades into darkness or resets in endless loops, our curiosity leaves a mark. The act of asking why is a kind of rebellion against entropy. It asserts that while everything may decay, meaning, however fleeting, can exist in the in-between. We may be brief flashes in the grand timeline of existence, but in asking these questions, we light up the dark. Of all the celestial phenomena that populate our universe, none are as mysterious and awe-inspiring as black holes. These cosmic monsters stretch the limits of physics, hiding their secrets behind a veil that no light can escape. To some, they represent the death of stars. To others, they may hold the key to unlocking new dimensions, parallel universes, or even time travel. But what exactly are black holes? At their core, black holes are regions of space where gravity has become so strong that nothing, not even light, can escape. They are formed when massive stars exhaust their nuclear fuel and collapse under their own gravity. This collapse creates a singularity, a point of infinite density, surrounded by an invisible boundary known as the event horizon. Once something crosses this event horizon, it is lost to the observable universe. No signal, no matter, no information can get out. This seemingly simple fact gives rise to some of the deepest puzzles in physics. One such mystery is the information paradox. According to quantum theory, information cannot be destroyed. But when matter falls into a black hole and is seemingly lost, where does its information go? Does it get preserved somehow on the event horizon? Is it encoded in subtle radiation? Or is it truly lost forever, violating the rules of quantum mechanics? This debate has consumed physicists for decades. Stephen Hawking famously proposed that black holes radiate energy due to quantum effects near the event horizon, a process now called Hawking radiation. Over immense spans of time, this radiation could cause black holes to shrink and eventually vanish. But if a black hole disappears, where does the information go? Does it escape with the radiation, get stored in some holographic format on the surface of the event horizon, or does it simply cease to exist? The implications are profound. If information is lost, it challenges the core of physics itself. If it's preserved, then black holes may be less like prisons and more like gateways, preserving cosmic memory in ways we've yet to understand. And then there's the tantalizing possibility of what lies inside. The singularity is a place where our current theories, general relativity and quantum mechanics, break down. Some physicists suggest that within a black hole, the fabric of space and time becomes so distorted that it could lead to a bridge, a wormhole, to another part of the universe, or perhaps another universe entirely. These theoretical structures, called Einstein-Rosen bridges, could, in principle, connect distant regions of space-time. But they come with extreme conditions. Tidal forces strong enough to spaghettify matter, radiation so intense it could vaporize anything approaching, and instability that might collapse the bridge before anything could cross. Still, the idea persists in science fiction and theoretical physics alike. What if black holes are not endpoints, but doorways, passageways through which matter, energy, or even consciousness might travel? More conservatively, black holes play a vital role in shaping the cosmos. Supermassive black holes, like Sagittarius A at the center of the Milky Way, govern the dynamics of galaxies, influencing star formation and galactic evolution. Some are millions or even billions of times more massive than our Sun, feeding on surrounding gas and dust in brilliant flares known as quasars. These luminous beacons outshine entire galaxies and offer glimpses into the early universe. In fact, astronomers now believe that black holes and galaxies co-evolve. As galaxies grow, so do their central black holes, suggesting a deep and mysterious relationship between cosmic structure and gravitational collapse. Black holes can also be detected through the powerful ripples they send through space-time, gravitational waves. In 2015, the LIGO Observatory detected these waves for the first time, produced by two black holes merging over 1 billion light-years away. This breakthrough confirmed a century-old prediction from Einstein's theory of relativity and opened a new era of astronomy, one where we can listen to the universe as well as see it. The gravitational wave detectors, LIGO, Virgo, and the upcoming LISA space mission promise to uncover many more secrets, revealing collisions, mergers, and perhaps even the moment a black hole is born. Despite their ominous reputation, black holes may also offer hope. Some physicists have proposed that in the distant future, highly advanced civilizations might harness black holes as power sources, using their immense gravitational energy to drive space travel or support life in a cooling universe. Others speculate that information from previous universes could be hidden within black holes, making them the ultimate vaults of cosmic history. And perhaps most intriguing of all, we may never fully know what lies inside of a black hole. Not because it's unknowable, but because reaching it may be beyond the limits of our technology, our physics, or even our minds. Black holes challenge our understanding of everything: time, space, matter, and information. They are cosmic riddles wrapped in paradox, forcing us to ask bold questions about the nature of reality itself. But maybe that's their greatest gift. Not destruction, but invitation. To probe deeper, imagine further, and wonder eternally. When we look up at the night sky, we perceive stars spread across the canvas of space. We imagine planets moving through voids, light traveling through nothingness. But what if space is not an empty stage, and time not just a ticking clock? What if they are both parts of a deeper structure? A fabric of reality we've only just begun to understand? This concept lies at the heart of Einstein's theory of general relativity, which revolutionized our view of space and time. Instead of treating them as separate entities, Einstein unified them into a single four-dimensional continuum known as space-time. In this model, massive objects don't simply exist within space. They bend it. They warp the geometry of space-time, and that warping is what we perceive as gravity. Picture space-time as a stretched rubber sheet. If you place a bowling ball on it, say a star, the sheet curves. Smaller objects, like planets, follow those curves. They don't feel a force pulling them. They're simply moving along the natural bends in space-time. This elegant insight explained everything from the orbits of planets to the bending of starlight near the sun. It even predicted the existence of gravitational waves, ripples in space-time itself, caused by massive events like black hole mergers, something we've now observed. But the fabric of space-time may be far more complex than a smooth surface. Physicists now suspect it may be quantized at the smallest scales, not continuous, but made of tiny, discrete units, much like pixels in a digital image. This idea is central to the search for a theory of quantum gravity, an elusive framework that would unify general relativity with quantum mechanics. One of the most compelling candidates for this unification is string theory. According to string theory, The fundamental building blocks of the universe are not particles, but tiny vibrating strings of energy. These strings can vibrate at different frequencies, giving rise to the particles we observe: electrons, quarks, photons, and more. But there's a twist. String theory only works if there are more dimensions than we can see. While we live in 3 dimensions of space and 1 of time, string theory suggests there are 10 or even 11 dimensions, most of them curled up at unimaginably small scales. These extra dimensions may help explain some of the deepest puzzles in physics, like why gravity is so much weaker than the other fundamental forces. If gravity is leaking into other dimensions, it might explain why it appears so faint in ours. The existence of hidden dimensions isn't just theoretical. Experiments at facilities like the Large Hadron Collider, LHC, are probing high-energy collisions to detect signs of extra dimensions. While no direct evidence has been found yet, the search continues. And the implications are staggering. If other dimensions exist, they could harbor entire realities, other universes with their own physical laws. This idea gives rise to the multiverse hypothesis, where our universe is just one of countless others. These universes may be separated not by distance, but by dimensions beyond our perception. Some physicists go further, suggesting that space-time itself might be an emergent phenomenon, not fundamental, but a byproduct of quantum entanglement. In this view, space and time arise from the way information is interconnected at the smallest scales. Reality, then, might be less like a solid stage and more like a vast quantum network, a hologram projected from deeper mathematical structures. This idea is supported by the holographic principle, which proposes that all the information contained in a volume of space can be represented on its boundary. It's as if our 3-dimensional universe is a projection of 2-dimensional data, a cosmic illusion with very real consequences. Incredible as it sounds, this principle has gained traction in black hole physics, where it helps resolve the information paradox by suggesting that data is stored on the event horizon. If true, it means that reality as we experience it might be encoded at the edges of our universe. These theories are bold, complex, and still evolving. They challenge our intuitions and force us to reimagine the very nature of existence. But they also hint at something beautiful, that the universe may be deeper, stranger, and more interconnected than we ever imagined. Perhaps we are like fish in a pond, sensing only the ripples on the surface, unaware of the vast ocean of dimensions just beyond our reach. Yet we are beginning to see patterns in the waves: gravitational lenses bending light, quantum entanglement connecting particles across the void, and the persistent hum of the cosmic microwave background, reminding us of our fiery origins. In this unfolding mystery, we are both explorers and part of the fabric itself. Our thoughts, our measurements, our questions, they are threads woven into the grand tapestry of space and time. The fabric of reality is not a backdrop, it is the story, and we are still writing it. Time. We experience it as a constant flow, a river that moves us from the past, through the present, and into the future. Yet, when we peer deeply into the fabric of the universe, a startling truth begins to emerge. Time may not be what it seems. In classical physics, time is treated as a simple, linear dimension, a parameter that helps describe motion. But in Einstein's theory of relativity, time is inseparably woven with space into a single fabric called space-time. And here, time behaves very differently depending on your perspective. One of the most profound consequences of relativity is that time is relative. It flows at different rates depending on your velocity and your position in a gravitational field. A clock on a satellite orbiting Earth ticks slightly faster than a clock on the ground. A clock near a black hole ticks far slower than one in deep space. These aren't just theoretical curiosities. GPS satellites, for example, must account for relativistic time dilation to maintain accuracy. Without adjusting for time shifts, your navigation system would quickly fail. This idea that time is not absolute leads to a radical proposition. There is no universal now. What you experience as the present may be in someone else's past or future, depending on where and how they are moving. Each observer carries their own slice of time, their own now moment. This has led some physicists to propose that past, present, and future all coexist, that time doesn't flow at all, but rather that we simply perceive it that way. According to the block universe theory, all events, from the birth of the universe to your next breath, already exist within the four-dimensional structure of space-time. You are not moving through time. You are inhabiting a moment in the block. Imagine a movie reel. The entire story is already there. Every frame, every scene, every ending. But as observers, we experience the movie one frame at a time, giving the illusion of motion and progression. The block universe challenges our intuitive sense of causality and free will. If the future is already written, can we truly make choices? Or are we simply experiencing a deterministic reality, playing out like a script? Some physicists argue that quantum mechanics restores our sense of freedom. In the quantum world, events don't have definite outcomes until observed. Particles exist in probabilities, in states of maybe rather than yes or no. This randomness suggests that the future is not fixed, but emergent, shaped by interactions and choices. But even here, things get stranger. The many worlds interpretation of quantum physics proposes that all possible outcomes of every event actually occur in branching parallel universes. In one reality, you turned left. In another, you turned right. In this multiverse of possibilities, every moment leads to a new world. Suddenly, time is not just a line, but a tree, branching infinitely into all potential timelines. In this view, the flow of time is simply our consciousness moving through one path among many. Other scientists explore time from the lens of thermodynamics, the arrow of time defined by entropy. The reason we remember the past but not the future is because entropy increases. We see broken eggs, but not unbroken ones leaping back together. This one-way direction gives time its forward bias, even if the fundamental laws of physics are reversible. So if entropy defines our sense of time, could a decrease in entropy reverse it? Theoretically, yes. But such conditions are so improbable in our universe that we never observe them. Even our brains are wired to process time as a flow. We store memories in one direction. We perceive motion as continuous. We make predictions and anticipate outcomes. Time feels real because our biology evolved in a universe where entropy increases and causality works. But what if that's an illusion too? Some philosophers and theoretical physicists now argue that time may not exist at all, at least not as a fundamental property of the universe. It may be emergent, arising from correlations between systems, or from the way we process information. The implications are staggering. If time is not fundamental, then reality may be more like a timeless structure, where all moments coexist and change is simply our perception of moving through them. This perspective may help reconcile the tension between general relativity and quantum mechanics. It offers a new way to understand black holes, cosmology, and even consciousness. In this view, life is not a journey through time, but a location in a vast, timeless landscape. Every moment you've ever lived or will live already exists. You are not passing through time, you are part of it. So what does this mean for us? It means that memory, identity, and meaning are not constrained to the ticking of a clock, that the moments you cherish, the laughter of a friend, the beauty of a sunset, the love of a parent, are etched into the fabric of space-time forever. You were there. You are there. You always will be. Perhaps the true mystery is not time itself, but our relationship with it, how we create stories, meanings, and futures from a universe that may already contain all its answers. And if all of time exists at once, then our curiosity, our hope, our drive to understand the cosmos, those too are timeless. When we gaze into the night sky, we often imagine the universe as vast and mysterious. But what if the most profound truth is not just how big it is, but how many of them there might be? What if our universe is just one among countless others, each with its own laws, histories, and possibilities? Welcome to the concept of parallel universes, a mind-bending idea that challenges the very meaning of existence. The multiverse, the idea that multiple universes exist beyond our own, is no longer confined to science fiction. It emerges naturally from several cutting-edge theories in physics and cosmology. Though still theoretical, each version paints a different, yet equally fascinating portrait of reality. Let's begin with the cosmic inflation model. After the Big Bang, our universe experienced a rapid exponential expansion known as inflation. Some versions of inflation theory suggest that this process didn't just happen once. Instead, it's eternal, continuously creating new bubble universes like ours in a vast cosmic foam. Each bubble may have different physical constants, different particles, or even entirely different dimensions. In this scenario, our observable universe is just a single bubble, a cosmic island in an ever-growing archipelago of universes. This is known as the eternal inflation multiverse. Then there's the quantum multiverse, born from the strange rules of quantum mechanics. According to the many worlds interpretation, every quantum event that can happen does happen, in separate, non-interacting branches of reality. When you flip a coin, both heads and tails occur, but in different parallel universes. This version of the multiverse suggests that every decision, every outcome, every possibility is realized somewhere. In one universe, you chose one path. In another, you made a different choice. Each branching creates a new timeline, a new version of you living a different life. Now consider string theory, which posits that the fundamental components of reality are vibrating strings, not point-like particles. In this framework, extra dimensions are required, 10 or 11 in total. The way these extra dimensions are curled up or shaped can produce entirely different physical realities, giving rise to what's called the landscape multiverse. There could be a nearly infinite number of possible universes, each with different physical properties. There's also the mathematical multiverse, proposed by physicist Max Tegmark. This theory suggests that any mathematically consistent structure exists as its own universe. In other words, if a universe is mathematically possible, then it exists somewhere. This radical view implies that reality itself is math, and that consciousness simply arises in those mathematical structures capable of supporting it. You exist not because of biology, but because your consciousness is a solution to a cosmic equation. One of the most poetic and speculative ideas is the brain multiverse, derived from M-theory. It suggests that our universe is a three-dimensional brain floating in higher dimensional space. Other brains could exist parallel to ours just millimeters away, but separated by dimensions we cannot perceive. Collisions between brains might even spark new Big Bangs, birthing entirely new universes. Our own Big Bang could have been such a collision, a moment when two brains smashed together in an invisible dimension beyond our own. So, if these other universes exist, why can't we see them? The simple answer is that they may be beyond our cosmic horizon, too far, too hidden, or too disconnected from our reality for light or information to reach us. These universes may follow different physical laws, making interaction impossible. Or they may exist in dimensions orthogonal to our own, forever out of reach. Yet we may find indirect evidence. Tiny fluctuations in the cosmic microwave background, the afterglow of the Big Bang, could reveal hints of other universes bumping into ours. High-energy experiments might produce particles that leak into extra dimensions. And quantum computing could test whether reality follows a single path or an ensemble of them. Even if we never observe another universe directly, the implications are staggering. In a multiverse, everything that can happen does happen somewhere. There may be a universe where dinosaurs never went extinct, where humans evolved wings, or where you made a single different decision and your life followed a new path. This can be overwhelming, even unsettling. It raises questions about fate, free will, and identity. Are you the real you, or just one version among infinite reflections? But the multiverse can also be deeply hopeful. If infinite realities exist, then so do infinite possibilities for creativity, for redemption, for discovery. Somewhere, you always have a second chance. Somewhere, the impossible is not just possible, it's inevitable. As we continue to explore the cosmos, we may never reach the edge of the multiverse, but we can explore its echoes in mathematics, in thought, and in the deepest questions we ask about our existence. Perhaps, in the end, the multiverse is not just a scientific idea, but a mirror reflecting the boundless curiosity of the human mind. We dream of other worlds because we are made of stars. And maybe, just maybe, the universe is dreaming with us. Across infinite skies. Among the stars, the galaxies, and the grand equations of physics, one mystery remains profoundly personal: consciousness. What is it? Where does it come from? And what is its place in the universe? Of all the phenomena we study, consciousness is perhaps the most elusive. We know it exists. We experience it every moment of our lives. But defining it, measuring it, or locating it in the cosmos is a challenge that transcends science and philosophy alike. What if the mind is not just a byproduct of the brain, but something deeper, something entangled with the fabric of the universe? Let's begin with the basics. In classical neuroscience, consciousness is thought to emerge from the brain's complex network of neurons. Billions of connections fire, organize, and synchronize to produce thought, memory, sensation, and self-awareness. This view treats consciousness as an emergent property, a result of intricate biological computation. But some scientists and philosophers argue that this explanation is incomplete. It describes the mechanics, but not the experience, the what it's like to be aware. This is known as the hard problem of consciousness, a term coined by philosopher David Chalmers. Why should physical processes give rise to subjective experience at all? To address this, some theories suggest that consciousness may be fundamental, not something that emerges from matter, but something that matter emerges within. One such idea is panpsychism, the view that consciousness is a basic feature of reality, like mass or charge. In this view, even the simplest particles may possess a primitive form of awareness, and complex consciousness arises from combinations of these building blocks. Then there's the Integrated Information Theory, IIT, which proposes that consciousness arises from the degree to which a system integrates information. According to IIT, consciousness isn't tied to biological neurons. It could, in theory, emerge in any sufficiently complex system, including artificial intelligence or even networks of particles. Some physicists go further, suggesting that consciousness and quantum mechanics may be connected. In the OR theory, proposed by Roger Penrose and Stuart Hameroff, consciousness arises from quantum processes in microtubules inside neurons. These quantum states might be sensitive to gravitational effects, linking awareness to the very structure of space-time. While this theory is controversial, it opens a profound question. Could consciousness and the universe be linked not just metaphorically, but physically? The anthropic principle adds another layer of intrigue. It observes that the universe seems precisely fine-tuned to allow for life and consciousness to exist. If the constants of nature were even slightly different, stars wouldn't form, atoms wouldn't bind, and minds wouldn't emerge. Some interpret this as a coincidence. Others see it as evidence that observers, like us, are not accidental, but essential. This leads to the provocative idea that the universe requires consciousness to exist. In some interpretations of quantum mechanics, an observer is needed to collapse probability into reality. Until observed, a quantum system exists in multiple states simultaneously. But when observed, it takes on a definite form. This has led some to ask, does the universe only become real when observed? While most physicists reject this as overly mystical, it remains a compelling philosophical puzzle. Are we passive witnesses of a vast universe, or active participants helping to shape it? Some thinkers even suggest that consciousness may be non-local, not confined to the brain or body, but part of a larger field, like gravity or electromagnetism. This idea is echoed in various spiritual and philosophical traditions, which describe the self not as a thing, but as a process of awareness flowing through the cosmos. If such a universal consciousness exists, whether emergent or fundamental, it reshapes our place in the universe. No longer isolated specks on a dust mote, we become nodes in a conscious network, the universe becoming aware of itself through us. Carl Sagan once wrote, "We are a way for the cosmos to know itself." In this view, consciousness is not separate from the stars and galaxies. It is their flowering. Life is not an accident, but an expression of the universe's own complexity, reaching a point where it can observe, wonder, and reflect. Even if we don't yet understand the full nature of consciousness, the very fact that we're asking these questions is remarkable. We are self-aware beings living in a reality filled with unknowns. And instead of retreating from them, we seek to understand. And perhaps that's the true essence of consciousness, the drive to explore, to connect, to create meaning in a cosmos that may or may not be listening. Whether the universe is conscious or not, it has given rise to consciousness at least once, here on a tiny planet orbiting an average star. That alone makes this universe profoundly special. So the next time you stare into the night sky, remember this. The same atoms that burn in stars are the atoms that form your thoughts. The light that crosses billions of years to reach your eyes does not just illuminate the past, it awakens something in you. Maybe the mystery of consciousness is not just to be solved, but to be honored. The stars stretch endlessly across the sky, each one a sun, many with planets, some perhaps like Earth. For centuries, humans have gazed upward and asked the most enduring question, are we alone? In recent years, this question has shifted from speculation to science. Advances in technology, astronomy, and astrobiology have turned the search for extraterrestrial life into a serious scientific endeavor. And with each discovery, the odds of alien intelligence existing somewhere in the cosmos grow harder to ignore. Let's start with the numbers. There are an estimated 100 billion galaxies in the observable universe, each containing hundreds of billions of stars. Many of those stars have planets. In fact, NASA's Kepler mission revealed that planets are more common than stars. Most stars host planetary systems, and a significant fraction may have Earth-like worlds in their habitable zones, where liquid water can exist. We now know of thousands of exoplanets, and among them, dozens appear potentially habitable. These are not fantasy anymore. They are real, measurable worlds. Some orbit red dwarf stars and may be tidally locked, with one face always facing their sun. Others are gas dwarfs or water worlds with deep oceans. Some, like Proxima Centauri b, orbit our nearest stellar neighbor, just 4.2 light-years away. So if habitable planets are plentiful, where are the aliens? This is the essence of the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" If intelligent life is common, why haven't we found any evidence of it? Why no signals, no ships, no visits? There are many possible answers, and none are fully satisfying. One possibility is that intelligent civilizations are rare. Life may be common, but intelligence may be an evolutionary fluke, a fragile anomaly rather than a natural outcome. After all, on Earth, life began billions of years ago, but complex intelligence only evolved once, very recently. Another idea is that civilizations destroy themselves. Advanced technology comes with existential risks: nuclear war, environmental collapse, artificial intelligence gone rogue. Perhaps most species don't survive long enough to become spacefaring. Then there's the great filter, the hypothesis that there is some step in the evolution of intelligent life that is extraordinarily difficult to pass. It could lie behind us, meaning we're rare survivors, or ahead of us, meaning we're doomed. Either possibility is sobering. Some scientists propose that alien civilizations are out there, but choose not to contact us. This is the zoo hypothesis, the idea that Earth is being observed, like animals in a cosmic preserve. Aliens may be waiting for us to reach a certain level of maturity before making contact. Others argue that we simply haven't been looking long enough, or in the right way. The universe is vast, and our search is still in its infancy. SETI, the search for extraterrestrial intelligence, scans radio waves for signals, but the frequency space is enormous, and our coverage is tiny. A civilization may have broadcast a message millions of years ago, but we weren't listening. Then there's the possibility that alien intelligence is unrecognizable. We often imagine aliens as biological beings with language and technology. But what if they're artificial, post-biological entities? What if they communicate through particles we can't detect, or think at speeds or scales we can't comprehend? Some scientists suggest that advanced civilizations may live in Dyson spheres, megastructures built around stars to harness their energy. These structures could be detectable through unusual infrared signatures, and surveys like WISE have searched for them. So far, no confirmed detections. Others propose the idea of alien megastructures orbiting stars. A few years ago, a star called KIC 8462852, or Tabby's star, showed strange dimming patterns that sparked speculation of artificial origins. While natural explanations now seem more likely, the event sparked renewed interest in searching for technosignatures, evidence of alien technology. Meanwhile, the search for microbial life continues closer to home. Mars, Europa, and Enceladus, with their subsurface oceans, are prime candidates. If we find even microbial life on another world, it will suggest that life is common and intelligent life may be inevitable given enough time. The discovery of alien life, even simple life, would reshape science, religion, and philosophy. It would tell us that we are not the center of the biological universe, that life is not a miracle unique to Earth, but a process that happens wherever conditions are right. But what if we never find aliens? What if we are alone? That too would be profound. It would mean that consciousness, imagination, and exploration are rare treasures, that we are the only eyes through which the universe sees itself. And with that awareness comes immense responsibility. Either way, alone or not, the search itself has value. It drives us to explore, to build telescopes, to study biology and chemistry and physics in new ways. It teaches us humility and wonder. It connects us across generations in a shared quest for answers. And perhaps one day we will look into the sky, receive a signal, and know we are not alone. Or perhaps we will become the ones to reach out, the first voices in a silent cosmos, lighting beacons that say, "We were here." The universe has a beginning, the Big Bang, a fiery origin that ignited space and time as we know it. But if there is a beginning, must there also be an end? While we often marvel at galaxies, stars, and the beauty of creation, the cosmos also holds a quieter, more haunting question. What happens when everything ends? What lies beyond the final flicker of the last star? To answer this, scientists explore the ultimate fate of the universe, and it's a story of staggering timescales, vast entropy, and the slow erosion of everything we know. Let's begin with what we understand. The universe is expanding. Since the Big Bang, space itself has been stretching, carrying galaxies farther apart. Not only is this expansion continuing, it's accelerating, driven by a mysterious force called dark energy. If this continues unchecked, the universe will grow colder, darker, and more isolated. Stars will burn out. Galaxies will drift beyond each other's light. Eventually, the night sky will go black, and the universe will enter a phase known as the degenerate era. This era, trillions of years from now, will be dominated not by stars, but by their remnants: white dwarfs, neutron stars, and black holes. The fusion fires of creation will be extinguished, and only the husks of stellar corpses will remain. Even these relics are not eternal. Over unimaginable timescales, white dwarfs will cool and fade. Neutron stars may collide or be swallowed by black holes, and black holes, once thought to be eternal prisons, will slowly evaporate through a process called Hawking radiation. This phenomenon, proposed by Stephen Hawking, suggests that black holes lose mass over time, emitting faint thermal radiation until, eventually, they vanish. It's an astonishing idea. The darkest, most powerful objects in the universe slowly leaking away into the void. In the distant future, this radiation will be the only source of heat and energy in a cosmos otherwise filled with silence. After the last black hole evaporates, a time known as the Dark Era, the universe will be left with only stray photons, low-energy particles, and possibly the faint echo of structure. Time will still pass, but nothing will change. No new stars, no new galaxies, just an endless expansion into cold infinity. This scenario is known as the heat death, or the Big Freeze, the most widely accepted model of the universe's end. It's not a cataclysm, but a fading. A universe that doesn't explode or collapse, but simply runs out of usable energy, reaching a state of maximum entropy. But is that the final word? Other models offer different possibilities. One is the Big Rip, a more violent ending. In this model, dark energy grows stronger over time, eventually overwhelming all forces. Galaxies are torn apart, stars shredded, even atoms ripped into their constituent particles. Space-time itself is pulled apart in a final, catastrophic moment. There's also the Big Crunch, a reversal of the Big Bang. In this scenario, expansion slows and reverses, and the universe collapses back into a singularity. Everything, galaxies, matter, even time, folds in on itself. Some see this as a precursor to a new Big Bang, part of an eternal cycle of cosmic birth and rebirth. Then there's the Big Bounce, a fusion of the Big Crunch and Big Bang ideas. Instead of ending, the universe rebounds, starting anew. This could mean that our current universe is just one in a long chain, each rising from the ashes of the last. Still more speculative is the vacuum decay scenario. Our universe may be in a false vacuum, a temporary energy state. If a more stable vacuum exists, a bubble of true vacuum could form, expanding at the speed of light and annihilating everything in its path. It would be sudden, silent, and unstoppable. Though terrifying, Vacuum decay is entirely possible within the laws of quantum field theory. But regardless of the model, the message is clear. The universe will not last forever. The stars will die. Matter will vanish, and time may itself lose meaning. This future may seem bleak, but it also carries beauty, because we are here now. We live in what scientists call the stelliferous era, the era of stars, a golden age of light, complexity, and life. An era when galaxies blaze, planets thrive, and intelligence has emerged, at least once. We live in the universe's most luminous moment. That fact alone is a miracle. We have the rare privilege of asking these questions, of studying the cosmos, imagining the future, and pondering our place within it. In doing so, we become part of the story. The universe, through us, becomes aware of its own destiny. And perhaps, awareness is its own kind of legacy. Even if everything ends, even if the stars go out and the galaxies fade, the act of wondering matters. It connects us to everything that was and everything that ever will be. Maybe the end of the universe isn't something to fear, but something to honor, a quiet epilogue to a grand and poetic journey. And maybe, just maybe, the end is not the end. The universe is vast, ancient, and filled with stars and planets beyond counting. The conditions for life seem to be scattered everywhere. And yet, across the black ocean of the cosmos, there is no sound, no signals, no messages, no contact. This quiet has become one of the most perplexing mysteries in science. The great silence, the apparent contradiction between the high probability of extraterrestrial life and the complete lack of evidence for it. This mystery echoes the famous Fermi paradox, but goes deeper. It's not just about the absence of visitors. It's about the eerie silence of the stars. Despite decades of listening with radio telescopes, searching with optical scans, and studying distant worlds, we've found nothing that definitively suggests intelligence beyond Earth. Why? There are many hypotheses, each fascinating, each unsettling in its own way. Some suggest that intelligent life is exceedingly rare. While microbial life might arise easily under the right conditions, the leap to tool-using, spacefaring intelligence may require a nearly impossible chain of evolutionary accidents. After all, Earth has been teeming with life for over 3 billion years, but only one species, humans, has built radio telescopes. Perhaps we are truly exceptional, a cosmic rarity. Others propose that intelligent civilizations tend to self-destruct. Technological progress may inevitably outpace wisdom. The moment a species gains the power to reshape its environment, it also gains the power to destroy itself. Nuclear war, climate collapse, artificial intelligence, these may be universal threats. This is the heart of the Great Filter hypothesis. Somewhere along the path from primitive life to interstellar civilization, there's a bottleneck, an almost insurmountable hurdle. If the filter is behind us, we are lucky survivors. If it lies ahead, our future may be in peril. But maybe the silence isn't because life is rare or doomed. Maybe it's because they're not talking. This brings us to the dark forest hypothesis, a chilling idea borrowed from science fiction. In a universe filled with unknown civilizations, the safest strategy may be to stay silent. Broadcasting your location could be dangerous. You never know who or what might be listening. Just as predators stalk silently in a forest, advanced civilizations may choose to observe but never reveal themselves. In this cosmic dark forest, survival requires discretion. Then there's the possibility that alien civilizations are talking, but we're not listening properly. Most of our searches assume alien signals would resemble human radio transmissions. But why would they? Advanced civilizations might use laser pulses, quantum entanglement, neutrino communication, or technologies we haven't even imagined. We may be looking for AM radio in a universe of encrypted quantum broadband. It's also possible that the window of detectability is small. Civilizations may only use detectable communications for a short time before switching to more efficient, undetectable methods. If their radio era lasts only a few hundred years, and they're thousands of light years away, we may miss each other entirely. Or perhaps we're simply too primitive. Imagine trying to explain the internet to a jellyfish. The gap between our understanding and that of a Type 2 or Type 3 Kardashev civilization might be so vast that we wouldn't even recognize their signals if they were all around us. We might be like ants trying to tune in to Wi-Fi. And there's always the possibility that we are alone. Not in the sense that life doesn't exist elsewhere, but that we are the first. In a universe 13.8 billion years old, intelligent life may only now be awakening. We may be the early ones, the first minds to ask questions, the first to build machines, the first to reach out. If that's true, then the silence isn't ominous. It's an invitation, a chance to become the signal, to be the first voice in the cosmic void, to light a beacon that says, "We are here." Already, efforts like Breakthrough Listen and SETI are scanning the skies for any signs. New instruments like the Square Kilometer Array will dramatically increase our sensitivity. We're entering an era where the silence may soon be broken or confirmed. But regardless of the outcome, the silence has already taught us something profound. It has forced us to look inward, to ask who we are, what kind of species we want to be, and how we would respond to finding others. It has reminded us that we are stewards of the only confirmed oasis of life in a vast desert of stars. And if the silence continues, maybe it's because we're meant to be the ones who fill it. With knowledge, with curiosity, with stories and songs, data and dreams, radio waves and gravitational messages. In a silent universe, every whisper matters. So we listen, we hope, and maybe one day, the silence will answer. What if everything you see, the stars, the earth, even your own body, isn't fundamentally real, but instead a kind of simulation? What if the universe itself is code, and we're all living inside a vast cosmic program? It may sound like science fiction, but the idea that reality could be simulated has gained serious attention among philosophers, scientists, and even tech billionaires. Known as the simulation hypothesis, this theory proposes that our universe might not be a physical reality at all, but rather a computational construct created by an advanced intelligence. One of the most famous proponents of this idea is philosopher Nick Bostrom, who in 2003 proposed a now famous argument. If any civilization reaches a point where it can simulate conscious beings inside a computer, and if it chooses to run such simulations, then the number of simulated realities could vastly outnumber real ones. Statistically, it may be more likely that we're in one of the simulations rather than in base reality. But what does this really mean? To explore it, let's first consider what a simulation requires: information, computation, and rules. If our universe behaves according to precise mathematical laws, which it appears to, then it may be computable. Quantum mechanics, relativity, entropy, all follow strict patterns that could be expressed algorithmically. Physicist John Archibald Wheeler once proposed the idea of it from bit, that all physical things emerge from binary information. If the fundamental layer of reality is data, then matter, energy, even space-time itself might be emergent phenomena, like pixels forming an image. But could a computer really simulate a universe like ours? Surprisingly, yes, in theory. The rules of physics could be programmed into a simulation with a finite amount of memory. Not everything needs to be calculated at once, only what's observed, like how video games only render what the player sees. Quantum mechanics may even support this. The famous double-slit experiment shows that particles behave differently when observed. Some argue this suggests the universe renders itself only when measured, like a simulation optimizing resources. Other oddities also raise eyebrows. The quantization of energy, the speed limit of light, and the Planck length, the smallest possible unit of space. These could be seen as signs of computational boundaries, limits that arise from discrete processing. Could such a system support consciousness? This is perhaps the biggest question. If consciousness is substrate independent, if it can emerge from patterns of information, then there's no reason it couldn't arise in a simulation, just as it does in a biological brain. This ties into current research in artificial intelligence and neuroscience, both of which suggest that awareness may be a product of information processing. If so, then simulated beings could be just as sentient as us, assuming the simulation is detailed enough. But who or what would run such a simulation? One possibility is that a post-human civilization, a society far more advanced than ours, could simulate its ancestors for research, entertainment, or even ethical purposes. These simulations might be indistinguishable from reality to those inside them. Alternatively, we may be part of a simulation running inside a natural universe, created by beings we cannot even comprehend. Some suggest we might be inside a nested series of simulations, like Russian dolls, one reality embedded inside another. So how would we ever know? There are some who believe we might detect glitches, anomalies in physics that betray the presence of underlying code. Others look for patterns in cosmic rays, the distribution of galaxies, or even the values of physical constants, hoping to find signatures left by the simulators. In 2017, a team at MIT proposed that if we are in a simulation, there might be limits to cosmic resolution, just like pixels in a screen. Simulating an entire universe requires shortcuts, and some believe we might eventually spot them. There's also the tantalizing idea that if the simulation is interactive, it may respond to deliberate experiments. What if we tried to communicate with the simulator? Would it reveal itself? Some scientists treat this with skepticism. They argue that the simulation hypothesis is unfalsifiable, that is, it can't be tested, and therefore doesn't count as science. Others see it as a modern version of age-old philosophical questions about illusion, perception, and reality. But even if we never prove we're in a simulation, asking the question changes everything. It forces us to reflect on what is real. If a simulated mind can feel pain, love, joy, and curiosity, are those experiences any less valid? If our memories, our choices, and our relationships exist within code, does that make them meaningless or infinitely precious? And what about morality? If we are simulated, are we being watched, judged, graded? Does the simulation have a purpose? Or is it random, a cosmic sandbox left running while its creators move on? If this is a simulation, then perhaps the most important thing we can do is prove ourselves worthy of the processes or cycles we occupy. To create, to connect, to explore, to be more than background code. Alternatively, maybe the simulation hypothesis is metaphor, a way to grasp the strangeness of reality. We live in a universe with mysterious rules, bounded constants, and seemingly arbitrary conditions. Whether it's a simulation or not, it feels programmed. And perhaps that's enough. Ultimately, the simulation hypothesis isn't about escaping reality, it's about understanding it more deeply. Whether we're in a simulation or not, we are thinking, feeling beings, capable of awe and imagination. And if that's all code, it's the most beautiful code ever written. Time. We experience it as a steady flow from past to future. We remember yesterday, live in the present, and anticipate tomorrow. But what if that flow could be bent, or even reversed? What if time travel isn't just the stuff of science fiction, but a scientific possibility? For centuries, time travel has captured the imagination. From H.G. Wells's classic The Time Machine to modern films like Interstellar and Tenet, the idea of moving through time like space is a recurring dream. But how close are we to making it real? Let's start with the basics. Einstein's theory of relativity. According to special relativity, time is not a universal constant. It dilates, slows down, depending on your velocity. The faster you move through space, the slower you move through time. If you could travel near the speed of light, time for you would pass much slower than for someone standing still. This phenomenon has been proven. Astronauts aboard the International Space Station, moving at high speed relative to Earth, age slightly more slowly than we do. It's not fantasy, it's measurable. This form of time travel is called time dilation, and it's real. So, in a sense, traveling to the future is possible. If you could build a spacecraft that travels at relativistic speeds, say 99.99% the speed of light, you could leave Earth for what feels like a few years and return to find centuries have passed. But what about the reverse? Traveling to the past? That's where things get tricky. According to general relativity, gravity also affects time. The stronger the gravitational field, the slower time flows. This is called gravitational time dilation, and it's most extreme near black holes. The film Interstellar dramatized this by placing characters on a planet orbiting close to a black hole, where 1 hour equaled 7 years in Earth time. Still, this only allows travel to the future, not the past. For backward time travel, we have to enter the realm of closed time-like curves, hypothetical paths through space-time that loop back on themselves. Einstein's equations do allow such solutions under specific conditions, like rotating black holes or massive cosmic strings. But these require exotic conditions, including negative energy or wormholes, which may or may not exist in reality. Wormholes, theoretical tunnels through space-time, could, in principle, connect different locations in time. If one end of a wormhole were accelerated to near light speed and then returned, the time difference between the two ends could allow travel from one era to another. But the challenges are staggering. Wormholes might collapse instantly. Stabilizing them would require exotic matter, a substance with negative mass. And even if one could be built, navigating it without being destroyed by radiation or tidal forces is another problem entirely. Still, the math doesn't rule it out, and where the math allows, imagination follows. Many physicists believe that quantum mechanics could hold the key. In quantum theory, particles can exist in multiple states at once. They can tunnel through barriers and appear in places they shouldn't be. Could time be another dimension we can tunnel through? Some speculative theories suggest that quantum entanglement could be linked to wormholes, forming ER equals EPR, a possible unification of general relativity and quantum mechanics. If so, space-time itself may be threaded with micro-wormholes, and time, in principle, may be more flexible than we imagine. Then there's the question of causality, the backbone of reality. If you go back in time and change something, what happens next? This leads us to the infamous grandfather paradox. If you travel back and prevent your grandfather from meeting your grandmother, would you cease to exist? One proposed resolution is the many worlds interpretation. In this view, every time you make a change in the past, you create a new branch of the universe. You don't erase your original timeline, you create a parallel one. You still exist, just in a different branch. This removes paradoxes, but introduces the idea of infinite realities, each with its own timeline, consequences, and futures. It's a beautiful and unsettling possibility. Others believe that time may be self-consistent. According to the Novikov self-consistency principle, any actions you take in the past were already part of history. No matter what you do, you can't change the outcome, because you already did it. In this view, time is not like a book you can rewrite. It's a sculpture already carved. Your journey back in time is just another part of that sculpture. But even if backward time travel proves impossible, the idea changes how we see reality. It forces us to question the flow of time, the nature of cause and effect, and our place in the fourth dimension. And maybe, just maybe, that's the point. Time travel isn't just about machines and paradoxes. It's about perspective. How we understand memory, anticipation, history, and choice. We are all time travelers, moving forward, second by second. What we do in that time defines our story. And who knows, in the distant future, civilizations far more advanced than ours may master space-time in ways we can't yet comprehend. They may send probes through wormholes. They may encode memories into tachyon streams. They may even loop back to observe their ancestors, us. If so, perhaps the UFOs we imagine, the dreams we have, the myths we tell, are shadows of those yet to come. Time is not just a line, it's a mystery, a canvas, a puzzle waiting to be solved, and we've only just begun to glimpse its possibilities. Time seems so simple. It flows like a river, always in one direction. We wake up, live, grow older, never younger. But why is this the case? Why does time only move forward and not backward? This question, deceptively basic, cuts to the heart of physics, cosmology, and the nature of reality itself. It touches everything from thermodynamics to consciousness. And while we live our lives assuming that time flows, science has shown that things are far more complex. At the core of this mystery lies the concept of the arrow of time, the idea that time has a preferred direction. In most of our everyday experiences, this direction is obvious. Eggs break but don't unbreak. Ice melts but doesn't refreeze spontaneously. People age but don't grow younger. This direction is closely tied to the second law of thermodynamics, which states that in any closed system, entropy, a measure of disorder, tends to increase over time. In other words, the universe naturally moves from order to chaos, from usable energy to unusable heat. This law gives time its arrow. It's not that the fundamental laws of physics require time to move forward. In fact, many equations, including Newtonian mechanics, Maxwell's equations, and even quantum mechanics, work equally well in reverse. If you recorded a billiards game and played it backward, the physics would still be valid. So why don't we see that happen in real life? Because while the laws of motion are reversible, entropy is not. As systems evolve, they become more disordered. And once that disorder increases, it's almost impossible to reverse. Think of mixing cream into coffee, technically reversible, but practically impossible. This suggests that the arrow of time is not a fundamental law, but an emergent property of thermodynamics. Time appears to move forward because the universe began in a highly ordered state, the low entropy beginning we call the Big Bang. But why was the early universe so ordered? This remains one of the deepest unsolved questions in physics. One possibility is that the initial conditions of the cosmos were just right, a unique configuration from which entropy could increase. Another view is that the arrow of time is tied to the expansion of space itself. As the universe expands, entropy grows, setting a direction for time to follow. There are even theories suggesting that the arrow of time may reverse in a contracting universe, or that multiple arrows of time may exist in different regions of a larger multiverse. In these speculative models, time might move backward elsewhere, or even loop back on itself. Quantum mechanics also raises profound questions. In the quantum world, particles exist in a state of superposition. only settling into a definite state when observed. Some interpretations, like the Copenhagen interpretation, suggest that the act of measurement introduces a kind of collapse, a transition from probability to reality. But again, the math doesn't require a direction. In fact, the Schrödinger equation, the central equation of quantum mechanics, is perfectly time-symmetric. So where does the asymmetry, the one-way flow, come from? Some researchers believe the key lies in the interaction between quantum systems and their environments, a process called decoherence. As quantum systems interact with the macroscopic world, they lose coherence and become classical, and in doing so, the system's entropy increases. Thus, decoherence may link the quantum and thermodynamic arrows of time. Consciousness also plays a role. Humans experience time subjectively, as memory, anticipation, and the sense of now. We remember the past, not the future. We can't unknow something we've learned. These asymmetries are built into our cognition and likely tied to entropy as well. Memory itself may depend on the irreversible flow of information, encoded by brain processes that rely on thermodynamic changes. We live forward in time because our biology, like the universe, runs on increasing entropy. But some thinkers go further. They ask, what if time isn't flowing at all? This leads to the idea of the block universe, a concept from relativity, in which all points in time exist simultaneously. In this view, the past, present, and future are equally real. We don't move through time. We simply experience different slices of a static four-dimensional structure. From this perspective, the arrow of time may be a psychological illusion, a function of consciousness moving through the block. We perceive time because we're built to do so, not because time flows. Still, whether time is flowing or we're moving through it, one thing is certain: the universe has a preferred direction. And that direction shapes everything we do, from how we build machines to how we define life itself. The arrow of time explains why we age, why we remember, why cause comes before effect. It underpins our laws, our stories, and our sense of identity. And yet, it might be one of the most fragile things in nature, arising from an initial state we don't fully understand. If the arrow of time can be reversed, altered, or even stopped, what would that mean for us? Could we rewind life like a tape, unmake decisions, undo mistakes, or would we simply vanish, our identities forever tied to the forward motion of thermodynamic time? These questions may never be fully answered, but in asking them, we deepen our understanding of existence itself. Because time is not just a number on a clock, it's the canvas of reality, the stage on which every moment, memory, and miracle unfolds, and the arrow that pierces through it all is still flying. The universe is vast, unimaginably vast. With trillions of galaxies, each containing billions of stars and likely billions of planets, the odds seem overwhelming. We shouldn't be alone. And yet, here we are, listening, searching, and hearing nothing. This contradiction is known as the Fermi paradox, the puzzle of why, in a universe so seemingly teeming with possibilities for life, we haven't detected any sign of alien civilizations. The paradox is named after physicist Enrico Fermi, who famously asked during a casual lunch conversation, "Where is everybody?" The logic is simple but powerful. If intelligent life is common in the universe, some civilizations should have emerged millions, even billions, of years before us. Given enough time, they could have spread across the galaxy, leaving behind evidence, signals, or even structures. But so far, nothing. No interstellar beacons, no megastructures, no confirmed alien transmissions, just a haunting silence. So where is everyone? Let's explore the leading explanations, each more intriguing and at times unsettling than the last. We are early. Maybe we're one of the first civilizations to emerge. The universe is around 13.8 billion years old. But life as we know it only appeared on Earth a few billion years ago. Intelligent life took even longer, mere blinks ago on a cosmic timeline. If conditions for intelligent life are rare or slow to develop, then perhaps we're the cosmic pioneers, the first to look up, to ask, to build. 2. Civilizations are rare. While microbial life may be common, complex life could be exceedingly rare. Earth required a precise set of conditions: a stable star, magnetic field, plate tectonics, a large moon, the right mix of elements. Even then, intelligence evolved only once, and barely. This idea is called the rare Earth hypothesis. It suggests that while the galaxy may be full of bacteria, technologically advanced life may be almost non-existent. 3. They're not using radio. We've only been broadcasting radio waves for about 100 years, a tiny window in cosmic terms. Other civilizations might use communication methods we can't detect, or they may have moved beyond electromagnetic signals entirely, into neutrino beams, quantum entanglement, or other exotic technologies. We may be listening on the wrong channel, like trying to hear a submarine with a walkie-talkie. 4. The Great Filter. Perhaps the reason we don't see others is because civilizations don't last. Somewhere along the path from simple life to spacefaring society lies a great filter, a nearly insurmountable obstacle. It could be nuclear war, climate collapse, AI takeover, or even cosmic events like gamma-ray bursts. If most civilizations self-destruct before achieving interstellar communication, then the silence isn't mysterious. It's tragic. But here's the catch. We don't know if the Great Filter is behind us or ahead. If it's behind us, perhaps in the leap from non-life to life, we may be special. But if it lies in the future, it could mean we're approaching a dangerous threshold. 5. They're avoiding us. This is the zoo hypothesis, the idea that advanced civilizations are aware of us, but deliberately avoid contact. Like humans observing animals in the wild, they might prefer not to interfere with our natural development. We may be quarantined, observed but untouched. The galaxy might be full of watchers, silently waiting for us to mature. 6. They're too alien. Perhaps we're expecting aliens to behave like us, to build radio towers, expand into space, or broadcast signals. But what if they're utterly different? Their minds, motives, and technologies might be unrecognizable. They might exist in dimensions we can't perceive, communicate via gravitational waves, or think on timescales of millennia. To them, we might be indistinguishable from background noise. 7. They were here and left. Some theories suggest Earth was visited long ago, before humans even evolved. Evidence of such visits may be lost to time, buried under tectonic plates, or vaporized by erosion. Others propose we've missed subtle signs, messages hidden in DNA, artifacts on the moon, or anomalies in our solar system. 8. We're in a simulation. If the universe is a simulation, then the absence of aliens might be by design. The simulation may be fine-tuned to focus on human development. Other civilizations could be non-playable, or simply not rendered. In this scenario, the Fermi paradox isn't a problem, it's a feature. 9. They're already here, and we can't see them. Some believe extraterrestrials could be among us, but invisible to our senses. They might exist as energy beings, AI intelligences in the asteroid belt, or life forms using forms of camouflage, or reality manipulation. Perhaps contact has occurred, but our understanding is too limited to recognize it. Regardless of the answer, the Fermi paradox forces us to ask, what kind of future do we want to build? Do we want to be the civilization that reaches out? That leaves traces for others to find? Or do we risk becoming a quiet planet, lost in the void? The silence of the stars is not empty. It's a question, and it waits for an answer. What does it mean to be an advanced civilization? We often think of ourselves as technologically sophisticated. We've built satellites, explored other planets, and even touched the edge of interstellar space. But in the grand scheme of the cosmos, where do we really stand? To answer this, Soviet astronomer Nikolai Kardashev proposed a bold idea in 1964, a way to classify civilizations based on the amount of energy they can harness. This became known as the Kardashev scale, and it provides a roadmap for the evolution of intelligent life. There are three main categories. Type 1, a civilization that can use all the energy available on its home planet. Type 2, one that can harness the energy of its entire star. Type 3, a civilization that can control the energy of its entire galaxy. Let's break this down. Type 1 civilization, planetary. This is the first major step toward cosmic maturity. A Type 1 civilization can capture all of the energy falling on its planet, including wind, solar, geothermal, and seismic power. It would control weather, earthquakes, and perhaps even volcanoes. It could terraform, stabilize climate, and manage natural resources at a global scale. Earth is not there yet. In fact, humanity currently sits around 0.72 on the Kardashev scale. According to physicist Michio Kaku, we're a transitional species, climbing the ladder toward full planetary mastery. To reach Type 1, we'd need to increase our energy consumption by several orders of magnitude while managing sustainability and avoiding collapse. Type 2 civilization. Stellar, a Type 2 civilization is truly interstellar. It can capture and utilize the full energy output of its parent star, about 10^26 watts in the case of the Sun. How would it do this? Enter the concept of the Dyson sphere, a megastructure or swarm of satellites surrounding a star to absorb its energy. It doesn't have to be a solid shell, as often imagined in sci-fi, but could be a dynamic orbiting cloud of solar collectors. A Type 2 civilization would no longer be bound to its home planet. It could colonize its solar system, mine asteroids, build planetary computers, and possibly shift the orbits of moons and planets to suit its needs. To us, such a civilization would be nearly godlike. Type 3. Civilization. Galactic. A Type 3 civilization can tap into the energy of an entire galaxy, around 10^36 watts. This means manipulating hundreds of billions of stars, building Dyson spheres across star systems, and managing interstellar travel on a massive scale. Such a species would be immortal in many ways, not as individuals, but as a civilization. They might evolve into a vast network of artificial intelligence, upload consciousness into energy fields, or become quantum civilizations. They would be capable of manipulating space and time itself, possibly even creating wormholes, altering dark matter, or engineering entire galaxies. We would be as microbes to them. Where are they? If such civilizations are possible, the question becomes, where are they? This loops us back to the Fermi paradox. Maybe Type 3 civilizations are rare. Maybe they collapse before reaching that level. Or maybe their activities are subtle, embedded in black holes, hiding behind energy cloaks, or operating in ways we can't comprehend. Some researchers search for Dyson swarms using infrared telescopes, hoping to detect the heat signatures of stellar-scale energy harvesting. So far, no confirmed detections exist, but our searches are just beginning. What lies beyond? The Kardashev scale doesn't stop at Type 3. Futurists have proposed Type 4 and Type 5 civilizations. Type 4, harnessing the energy of the entire universe. Type 5, controlling the multiverse, multiple universes, perhaps outside our physical laws. These are wildly speculative. But as physics pushes into quantum gravity, string theory, and higher dimensional space, the notion of multiverse engineering becomes more than pure fantasy. The risks of advancement. Climbing the Kardashev scale isn't without danger. Each leap in energy use brings potential for self-destruction. A Type 1 society must avoid climate collapse, nuclear war, and AI domination. A Type 2 could trigger solar catastrophes. A Type 3 might flirt with galactic instability. Technological power must be matched with ethical evolution. We might be tested, over and over again, by the very tools we create. Why it matters. The Kardashev scale isn't just a classification, it's a vision. It reminds us that civilizations evolve, not just culturally, but cosmically. It gives us a benchmark, a direction, a sense of what lies ahead if we survive long enough. It also humbles us. We are infants on the cosmic stage, but we are growing, slowly, painfully, beautifully. Will we rise, or will we vanish? Another echo lost in the stars? The choice for now is ours. The universe is 13.8 billion years old, but the most dramatic moment in its history may have occurred in the very first split second, a moment so fast, so explosive, and so strange that it reshaped everything. This moment is known as cosmic inflation. It's a theory that proposes the universe expanded faster than the speed of light in the tiniest fraction of a second after the Big Bang. And while it sounds unbelievable, cosmic inflation helps solve some of the deepest puzzles in cosmology, including why the universe looks the way it does today. Let's step into the beginning of everything. What is cosmic inflation? According to the standard Big Bang model, the universe began as a singularity, a point of infinite density and temperature. But this model raised several big questions. Why is the universe so uniform in all directions? Why is the geometry of space so flat? And why are there no magnetic monopoles or exotic relics from early physics? These mysteries are known as the horizon, flatness, and monopole problems. In the 1980s, physicist Alan Guth proposed inflation as a solution. The idea, a mysterious field, called the inflaton field, caused space itself to undergo exponential expansion. In less than a trillionth of a second, the universe grew by a factor of at least 10 to the 26. That's like blowing up a proton-sized speck to the size of a galaxy, instantly. Why it matters. Inflation solves the horizon problem by explaining how distant regions of the universe could have once been in contact before being blown apart. It explains the flatness problem because inflation would smooth out any initial curvature, and it dilutes any unwanted relics like monopoles. But more importantly, inflation made the universe predictable. Tiny quantum fluctuations in the inflaton field were stretched by inflation into cosmic seeds, slight density differences that eventually grew into galaxies, stars, and planets. In essence, quantum noise became the structure of the universe. This is one of the most profound ideas in science, that randomness at the smallest scale shaped the largest structures in existence. After inflation, reheating? When inflation ended, the inflaton field decayed, releasing a massive amount of energy and reheating the universe. This kicked off the hot Big Bang as we understand it, filling space with particles, radiation, and light. From there, the universe continued to expand, but at a much slower rate. This sequence, inflation, reheating, and expansion, sets the stage for everything. Atoms, chemistry, galaxies, life. Is inflation proven? Inflation is elegant, powerful, and widely accepted, but it's still a theory. We don't know exactly what the inflaton is. It hasn't been directly observed. And other models, like cyclic universes or bounce cosmologies, offer alternative explanations. However, cosmic microwave background (CMB) observations have strongly supported inflation's predictions. The CMB is uniform, with tiny fluctuations that match inflation models. The flatness of space is confirmed to extreme precision. The large-scale structure of the universe aligns with quantum inflationary seeds. In short, the data fits, but we still don't know why inflation happened. Searching for proof, one of the smoking guns for inflation would be the detection of primordial gravitational waves, ripples in space-time generated by inflation itself. In 2014, the BICEP-2 experiment made headlines by announcing such a discovery. But later analysis showed the signal was likely due to galactic dust, not primordial waves. Still, the search continues. Experiments like LIGHTBIRD, Planck, and the Simons Observatory aim to detect the faint B-mode polarization in the CMB, a potential fingerprint of inflation. If detected, it would not only confirm inflation, but offer a glimpse into physics at 10^35 seconds after the universe began, far beyond any particle accelerator. The multiverse connection. Some versions of inflation, known as eternal inflation, suggest that while our universe inflated and slowed down, other regions kept inflating forever. This leads to the idea of a multiverse, a vast collection of universes, each with different physical constants, dimensions, or even laws of physics. In this view, our universe is just one bubble in a cosmic foam, a small part of a much larger reality. This has profound implications. It may explain why our universe seems fine-tuned for life. In the multiverse, we just happen to be in a region where life is possible. But it also raises deep questions about what's testable, observable, and even real, what it means for us. Cosmic inflation is not just about numbers or equations. It's about origins. It tells us that the universe didn't just begin. It began with a bang, followed by a blow-up, setting the stage for everything to follow. It also reminds us of how much we still don't know. What caused inflation? What is the inflaton? Did inflation ever stop? Could it happen again? And if we live in one bubble, what lies beyond? These are no longer just philosophical questions. They're scientific ones. And in seeking the answers, we're reaching toward the very birth of reality. Imagine looking up at the stars and galaxies scattered across the night sky, believing we understand the cosmos. But what if we told you that everything we can see, stars, planets, galaxies, makes up less than 5% of the universe? The rest? It's invisible, unseen, mysterious. Welcome to the world of dark matter, one of the greatest puzzles in modern physics. Despite being invisible, it holds galaxies together, shapes the universe's structure, and outweighs normal matter by more than 5 times. But we've never seen it, never touched it, never directly detected it. So what is dark matter? And why does it matter? Let's dive deep into the cosmic shadows. The evidence for dark matter. The first clues emerged in the 1930s, when astronomer Fritz Zwicky noticed something strange. He was studying the Coma Cluster, a group of galaxies, and realized they were moving too fast to be held together by the visible matter alone. Something else, something invisible, must be providing extra gravity. Later, in the 1970s, Vera Rubin made groundbreaking observations of galaxy rotation curves. Instead of stars moving slower at the edges, as Newtonian physics predicts, they were moving at constant speeds, as if an unseen mass surrounded them. That mass? Dark matter. Since then, countless observations, from gravitational lensing to cosmic microwave background, CMB studies, to galactic formation models, have confirmed the presence of dark matter. What is it made of? That's the trillion-dollar question. Dark matter doesn't emit light, doesn't absorb radiation, and barely interacts with normal matter. But it exerts gravitational pull, shaping galaxies and clusters. Scientists have proposed several candidates. WIMPs, weakly interacting massive particles. Hypothetical particles that rarely interact with normal matter. They were long considered top contenders, but so far, no direct detections have occurred. Axions, ultralight particles that might solve problems in quantum physics and also account for dark matter. Sterile neutrinos, a hypothetical version of the neutrino that doesn't interact via the weak force. Primordial black holes. Formed in the early universe, these tiny black holes could contribute to the dark matter density. Despite decades of research and high-tech experiments, we still don't know the exact nature of dark matter. How do we search for it? Physicists and astronomers use multiple methods. Direct detection. Instruments buried deep underground, like Xenon-NT and Lux-Zeppelin, aim to catch dark matter particles colliding with atoms. So far, the results have been null, but the hunt continues. Indirect detection. Looking for annihilation signals, when dark matter particles collide and produce gamma rays or neutrinos. The Fermi Gamma Ray Space Telescope has looked toward the galactic center for signs. Particle colliders. At places like CERN's Large Hadron Collider, scientists hope to create dark matter particles through high-energy collisions. Any imbalance in energy might hint at invisible particles escaping. Astrophysical observation. By observing galaxy mergers, gravitational lensing, and cosmic structure, scientists infer where dark matter is concentrated. Despite the elusiveness, every null result sharpens our models and narrows the possibilities. Why it's important. Dark matter isn't just a curiosity. It's fundamental to understanding the structure and evolution of the universe. Without dark matter, galaxies wouldn't hold together. They'd fly apart under their own rotation. Large-scale cosmic structures wouldn't exist. Dark matter's gravitational pull acts as scaffolding for galaxies to form. The universe's expansion wouldn't match observations. Dark matter influences how the cosmos evolved after the Big Bang. In short, dark matter is the invisible glue that holds the universe together. What if it doesn't exist? Some theories suggest we've misunderstood gravity itself. One alternative is modified Newtonian dynamics, OND, which proposes that at very low accelerations, gravity behaves differently than predicted by Newton or Einstein. MOND can explain some galactic behavior without invoking dark matter. However, MOND struggles with cluster dynamics and cosmic background data. Most cosmologists still support the dark matter hypothesis. Dark matter and the future. If we ever identify dark matter's true nature, it could open entirely new realms of physics. Perhaps new forces, new particles, or even a dark sector, a shadow version of our universe with its own interactions, atoms, and complexity. Some even speculate that dark life could exist, organisms based on dark matter physics, invisible to us. While purely speculative, it reminds us that our understanding of the universe may be as limited as a fish trying to comprehend the ocean's surface. What lies ahead? As telescopes grow more powerful and detectors more sensitive, we edge closer to unveiling this invisible puzzle. Projects like the James Webb Space Telescope, Euclid, and the Vera C. Rubin Observatory will help map dark matter through gravitational lensing and cosmic structure. And perhaps, one day, we'll not just detect dark matter, but use it, manipulate it, or even build with it. But for now, it remains a ghost, ever present, ever elusive, a silent architect of the cosmos. When you look at the night sky, you see stars and galaxies scattered across the darkness, random, beautiful, but seemingly chaotic. But if you could zoom out far enough, Beyond the scale of galaxies, clusters, and even superclusters, a hidden order would emerge. An enormous, interconnected structure, like a spider's web woven from galaxies and gravity. This is the cosmic web, the vast skeleton of the universe. It stretches across billions of light years, made of filaments of dark matter, gas, and galaxies, interspersed with massive voids, empty expanses where few galaxies exist. It's the universe's large-scale structure, and understanding it reveals deep truths about how the cosmos evolved. A universe of structure. Shortly after the Big Bang, the universe was hot, dense, and nearly uniform, except for tiny quantum fluctuations. These minute variations in density became the seeds of all future structure. As the universe expanded and cooled, gravity amplified the denser regions, pulling in more matter and forming the first stars and galaxies. Over billions of years, this process created galaxies, clusters of galaxies, superclusters, and eventually the cosmic web, the largest pattern in the universe. Today, massive filaments stretch like tendrils across space, connecting galactic clusters. At the intersections of these filaments lie the most massive structures, nodes, where clusters merge and collide. And in between, enormous voids, often hundreds of millions of light-years across, almost completely empty. Mapping the invisible. We can't see the cosmic web with our eyes, but we can trace its outlines. Telescopes like Sloan Digital Sky Survey, SDSS, and upcoming missions like Euclid and the Vera C. Rubin Observatory scan the skies, mapping the positions and redshifts of millions of galaxies. These galaxies serve as markers, revealing the underlying structure. But the true scaffolding of the web isn't made of stars. It's made of dark matter. Simulations like the Millennium Simulation and Illustris TNG show how dark matter forms long filaments, with galaxies forming along them. This web-like pattern arises naturally from the physics of gravity and the distribution of matter after the Big Bang. It's a cosmic fingerprint. Studying the web, astronomers and physicists use the cosmic web to test theories about dark matter and how it interacts, dark energy and how it affects cosmic expansion, neutrino mass, which influences structure formation, primordial fluctuations from the Big Bang. By analyzing the geometry, growth, and distribution of the web, scientists can reverse engineer the forces that shaped the cosmos. It's like reading the history of the universe in a vast, invisible script. Cosmic filaments and the warm-hot intergalactic medium, WEM. Within the web's filaments lies a puzzle, the missing baryons. Astronomers know how many protons and neutrons should exist, but nearly 40% of them are unaccounted for. Where did they go? The answer may lie in the warm-hot intergalactic medium, or WIM. This is gas at temperatures of 10^5 to 10^7 Kelvin, stretched along the filaments of the cosmic web. Recent observations using X-ray telescopes like Chandra and ESA's XMM Newton have begun detecting this hot gas, confirming that the WHIM may indeed house the universe's missing normal matter. This gas is too diffuse to form stars, but it's critical to understanding how galaxies evolve. Cosmic web and life? The cosmic web isn't just a structure. It may influence where life can arise. Galaxies near the nodes, where filaments intersect, tend to be larger, older, and richer in elements needed for planets and biology. Meanwhile, galaxies deep within voids are often smaller, younger, and less chemically evolved. This suggests a cosmic bias, where some regions of the universe are more likely to harbor complex life than others. Some even speculate that our place in the web, not too close to chaos, not too far from richness, is part of the anthropic principle. We exist in a region where conditions allow observers to emerge. Could it be conscious? Here's a strange idea. The structure of the cosmic web, with its branching filaments, nodes, and signals, has been compared to neurons in the human brain. A 2020 study found that the topology of the universe and the brain's neural network are strikingly similar, both displaying a balance of information flow and clustering. Is it coincidence? Or could the cosmos be conscious in some way? A thinking structure, not in the traditional sense, but as a system of emergent complexity. We don't have answers, but the comparison stretches our imagination. What it teaches us. The cosmic web teaches us that the universe is not random. Even across billions of light years, there is structure, order, and beauty, sculpted by gravity, time, and the physics of the early universe. It also reminds us how small we are. Our galaxy is just one bead on a filament, one dot in a sea of voids and clusters, part of a structure so large it takes light billions of years to cross. But in mapping this web, in understanding its intricacies, we fulfill a deeply human purpose. To find patterns, to discover meaning, to see the invisible, and know we're part of something far grander than ourselves. When you look at the night sky, you see stars and galaxies scattered across the darkness. Random, beautiful, but seemingly chaotic. But if you could zoom out far enough, beyond the scale of galaxies, clusters, and even superclusters, a hidden order would emerge. An enormous, interconnected structure, like a spider's web woven from galaxies and gravity. This is the cosmic web, the vast skeleton of the universe. It stretches across billions of light years, made of filaments of dark matter, gas, and galaxies, interspersed with massive voids, empty expanses where few galaxies exist. It's the universe's large-scale structure, and understanding it reveals deep truths about how the cosmos evolved. A universe of structure. Shortly after the Big Bang, the universe was hot, dense, and nearly uniform, except for tiny quantum fluctuations. These minute variations in density became the seeds of all future structure. As the universe expanded and cooled, gravity amplified the denser regions, pulling in more matter and forming the first stars and galaxies. Over billions of years, this process created galaxies, clusters of galaxies, superclusters, and eventually the cosmic web, the largest pattern in the universe. Today, massive filaments stretch like tendrils across space, connecting galactic clusters. At the intersections of these filaments lie the most massive structures, nodes, where clusters merge and collide. And in between, enormous voids, often hundreds of millions of light years across, almost completely empty. Mapping the invisible. We can't see the cosmic web with our eyes, but we can trace its outlines. Telescopes like Sloan Digital Sky Survey, SDSS, and upcoming missions like Euclid and the Vera C. Rubin Observatory scan the skies, mapping the positions and redshifts of millions of galaxies. These galaxies serve as markers, revealing the underlying structure. But the true scaffolding of the web isn't made of stars. It's made of dark matter. Simulations like the Millennium Simulation and Illustris TNG show how dark matter forms long filaments, with galaxies forming along them. This web-like pattern arises naturally from the physics of gravity and the distribution of matter after the Big Bang. It's a cosmic fingerprint. Studying the web, astronomers and physicists use the cosmic web to test theories about dark matter and how it interacts, dark energy and how it affects cosmic expansion, neutrino mass, which influences structure formation, primordial fluctuations from the Big Bang. By analyzing the geometry, growth, and distribution of the web, scientists can reverse engineer the forces that shaped the cosmos. It's like reading the history of the universe in a vast, invisible script. Cosmic filaments and the warm-hot intergalactic medium, WEM. Within the web's filaments lies a puzzle: the missing baryons. Astronomers know how many protons and neutrons should exist, but nearly 40% of them are unaccounted for. Where did they go? The answer may lie in the warm-hot intergalactic medium, or WIM. This is gas at temperatures of 10^5 to 10^7 Kelvin, stretched along the filaments of the cosmic web. Recent observations using X-ray telescopes like Chandra and ESA's XMM Newton have begun detecting this hot gas, confirming that the WHIM may indeed house the universe's missing normal matter. This gas is too diffuse to form stars, but it's critical to understanding how galaxies evolve. Cosmic web and life? The cosmic web isn't just a structure. It may influence where life can arise. Galaxies near the nodes, where filaments intersect, tend to be larger, older, and richer in elements needed for planets and biology. Meanwhile, galaxies deep within voids are often smaller, younger, and less chemically evolved. This suggests a cosmic bias, where some regions of the universe are more likely to harbor complex life than others. Some even speculate that our place in the web, not too close to chaos, not too far from richness, is part of the anthropic principle. We exist in a region where conditions allow observers to emerge. Could it be conscious? Here's a strange idea. The structure of the cosmic web, with its branching filaments, nodes, and signals, has been compared to neurons in the human brain. A 2020 study found that the topology of the universe and the brain's neural network are strikingly similar, both displaying a balance of information flow and clustering. Is it coincidence? Or could the cosmos be conscious in some way? A thinking structure, not in the traditional sense, but as a system of emergent complexity. We don't have answers, but the comparison stretches our imagination. What it teaches us. The cosmic web teaches us that the universe is not random. Even across billions of light years, there is structure, order, and beauty, sculpted by gravity, time, and the physics of the early universe. It also reminds us how small we are. Our galaxy is just one bead on a filament, one dot in a sea of voids and clusters, part of a structure so large it takes light billions of years to cross. But in mapping this web, in understanding its intricacies, we fulfill a deeply human purpose: to find patterns, to discover meaning, to see the invisible, and know we're part of something far grander than ourselves.